Hello everyone and thank you for joining us today. Welcome to Megger's Day 1 of the Virtual Substation BPS. My name is Michael Fleischer and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenters. Today we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. The presenter for our first segment today is Volney Naranjo, Senior Applications Engineer. Also, to assist with the question and answer session, we will have two panelists joining us today. Daniel Carreño, Applications Engineer, and Sanket Bolar, Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Volney.
Thank you very much, Michael, and thank you to all the attendees for coming to this virtual best practices seminar. The idea is that you learn and go through a lot of technical information today, and feel free to ask questions so we can help you at the end of the webinar, or later on we can send the answers via email. So in my presentation, we're going to talk about the procedures and tools for battery load testing. We're going to be seeing some of the basic details at on Andy's presentation, and well, I am covering some basic concepts related to the battery load testing here, and we are also going to talk about the different standards that are available for battery testing, for the load testing of batteries. And then we're going to focus mainly on the IEEE recommendations. And once we have done covered that part, we're going to see how to run a test, or what are the implications of running a test. It's a very basic concept about the load testing of a battery, but running the test has a lot of implications that we want to cover. And then to finalize, we are going to see what a result or a test report should look like, what information it should contain, and also we want to discuss the tools that you want to use for the testing. So on the basic concepts, we want to cover a couple of things in addition to the introduction on these basic concepts to understand and to go over the procedures of battery testing. But before we go into that, batteries are definitely a very important asset. They are an energy storage device that dies naturally, and they have a set span of time. When you buy a battery, it will be 20 years rated, or 15 years rated. So, and that is pretty much kind of very accurate. And you want to know how or when, in what type of or stage of the life of the battery you are, or if that battery is degrading very fast. You want to see in what part of this curve that we have here that battery is going to be. So these operating, the life expectancy is really affected by the operating or the maintenance conditions, and being batteries a critical component of the electrical system, it requires a lot of maintenance and very good maintenance practices, more than a lot, very good maintenance practices to achieve that life expectancy. And if you monitor that progress of the deterioration or the degradation of the life of the battery, you can improve your battery maintenance procedures. And that is the intent of these two technical presentations that we are having today, that you can incorporate or understand very well the battery and the maintenance procedures, and you can incorporate those into your maintenance practices. There are several maintenance testing methods that are available to try to identify what is the condition of the battery. A very basic one is float current. Also ohmic testing, it's another very good test, which Andy is going to cover. And then load testing. Now, load testing is the only test that can tell you what is the real condition of the battery. So load testing is the only proven method to determine the capacity of the battery. To measure that remaining capacity in the battery is you want to use the load test. This is also a way to see the true state of health, see what is the condition at a certain time in the life of the battery, and basically it tells you the remaining life. Battery will come with 100% capacity or even higher capacity, and you as you test and you get that remaining capacity, there's going to be a point where you have to replace the battery. The capacity is not reduced down to zero. Really, there's a criteria there that we want, that we are going to be talking about. So that tells you the remaining life. Despite or the being this the main test that you can perform, really it's a test that it's load, it's resource and time demanding. You need to have a very good understanding of the procedures and use the adequate tools to run the test. So that's why we're presenting all of this information. And we're going to focus mainly on vented lead acid batteries, VLA, valve regulated lead acid batteries, VRLAs, and nickel cadmium batteries, and all of these is related to IEEE procedures. So the capacity test, what is the capacity of a battery? So it is the quantity of electricity or the energy that a battery can deliver or that it can store. And it's usually expressed in amp hours, and this capacity will depend on the amount of active material. As the battery ages, as time passes, that active material deteriorates or degrades or gets dissolved into the chemistry of the battery, and that amount of capacity that it can store or the amount of energy that it can store gets reduced. Like the images that I have here show, you start kind of losing volume in that tank that the battery represents. So basically, you lose the space that you have available to be able to run a test, to store energy. And that's what you want to measure. You want to know what percentage of capacity you are in a battery. And as said before, the maintenance and operation affect this quality. Now, there's a concept or a term that we use a lot in batteries is what is the nominal capacity. So nominal capacity is the quantity that is used to identify a battery. Whenever you buy a battery or whenever you talk to a manufacturer, there's kind of a reference value, and that is the nominal capacity. This value corresponds typically to 8 or 10 hours. And but one very important aspect to consider is that this is not the only rate to consider on a battery. There's another term that it's very common with batteries, which is rated capacity. That they are kind of synonyms, and many times in other equipment they represent the same thing. Here there's a little bit of a difference, and that's why we are defining this here. So in this case, for example, I'm showing here a picture of a battery that has a nominal capacity of 365 amp hours. Then I have one more here that is 1960, and one more here which is a 110 amp hour battery. And here we see more details related to the nameplate. But the main point here is this is the nominal capacity that the manufacturer is using to identify the capacity of that battery. However, if we go a little bit more in detail, there are really more rates that you can get, or more capacities that you can get from that battery. And that is what is called the rated capacity, which is the quantity of electricity that the manufacturer declares that a battery can deliver under specified conditions. So again, as the same that the nominal capacity was indicated for 8 hours, and one nameplate was showing us some temperature, that is the rated capacity. That the same concept is used to define the rated capacity. You need to define the rated capacity to an end voltage, a reference temperature, and a specific duration. And usually that end voltage is basically the end of discharge. So that is an important piece of information for a load test. So here we can see one example. This is a battery that the nominal capacity is represented here as 200 amps hour. And if we think on the reference time, it is 8 hours. So 8 hours times 25 amps, continuous amps, that would be the 200 amps hour. However, there's more ratings that you can get from this battery, and that would be the rated capacity, and this would be selected according to the duty cycle of the battery. So bottom line here is that you may be getting to to test a battery, and you should not test to the nominal capacity. You should test to the rated capacity that the battery was really calculated or was designed. And that is a very important piece of information when running a test. This is another example. Another manufacturer has the table with the voltage level, with the minimum voltage or the end of discharge voltage, temperature reference, and the different times that you can get from this battery. So these tables are not there for convenience of testing at different rates according to our needs or our requirement or our conditions of load bank or time availability. These tables are there to be able to test according to the duty cycle of the battery. And one more term is the state of charge, is the amount of energy stored at a given moment in the battery. So this is the typical indicator that we look at our cell phones to see how much energy I have stored, but it's not a measurement of the quantity of energy that it can store. It is determined by the charging current or float voltage or the float current or the specific gravity, and this will depend on the battery chemistry, on the battery material. And it's really not that easy to determine sometimes. And well, it's mainly when the battery reaches the floating conditions. And so you can see here a representation of a battery that is fully charged, partially discharged, or fully discharged. And well, this last representation is not the reality for VLA batteries. They never should go to zero voltage. So again, this does not indicate the capacity, and but one very important thing is that the battery has to be fully charged for proper capacity test. So when you're going to run the test, the battery has to be fully charged, and there's actually a full procedure of preparation, and we're going to go over that. And just one more slide to reinforce the two concepts. So you can have a battery that is discharged or fully charged, or that is charged with some capacity loss, or the three conditions. It's partially discharged, 90% capacity because there's some degradation there, and you can see these comparison here. So let's go into the maintenance standards. There are different documents, mainly from IEEE. We have the VLA battery standard, the recommended practice for maintenance, testing, and replacement of VLA batteries. It's IEEE 450, and the same document is available there for the vented nickel cadmium, the 1106 standard, and IEEE 1188, which is for valve regulated lead acid batteries. The three documents, when they talk about the capacity testing, they're very similar. There are some details that are different, related, or will be different due to the nature of the battery, the different characteristics of the battery, but in general, the test methods are very similar. And there's one more standard there for UPS systems, 1184, in which you need to test the battery also, not only the battery, but the AC system. You need to test the inverter. Here in the US and Canada, we need to also go with the NERC requirements. We need to test as per the schedule of the NERC requirement, and that's important because that defines how often to test the batteries. And so we're not covering that here. We have extensive information in that if you need it. And well, the same that there's the IEEE standards in the IEC world, we have two more standards, one for vented lead acid and one for valve regulated, and there's also one more for nickel cadmium. So in this presentation, or these documents, the IEEE documents, they are divided in different sections. Mainly they cover safety, maintenance, inspections, and corrective actions. They talk about the type of load test, schedule, procedures for load test, and the battery replacement criteria. And There's also recommendations about the recycling and the disposal, spill containment, and very good annexes. In this presentation, we are focusing on the 4 bullet points that are highlighted there in yellow, and that with that, we move on to the type of tests. So there are 4 basic type of tests defined in the standard that you will perform according to the stage of the life of the battery, or depending on the type or the information you want to get from the test. So the very first one is the acceptance test. It's ideal to run a test at the beginning of the life of the battery. And this would be a test that you perform at the factory or upon installation, usually in the very first 6 or probably even the first year of the life of the battery. When you run the test, you run it to a specific constant discharge rate and duration, and it's usually a test that you perform to verify that nominal capacity, whatever the nominal capacity of the battery is, or depending on what are the requirements, you may select a different rate, but it has to be very well discussed and defined with the owner and the supplier of the battery. Then the purpose of the test is to measure the capacity of the battery, the percentage capacity, and a result of 90% is acceptable. That's typical to see. Batteries, especially the vented lead acid batteries, they start to develop their capacity once you pour the acid in. So if you test the battery too soon after installation and not having been under floating conditions for a while, then it's not going to show 100% capacity, but that capacity can increase after some time. Then when you want to get the calculation for the capacity, there's 2 different methods in the standard, and we're going to be talking about them. When you do the acceptance test, you need to use the time adjusted method to generate the result, to calculate the capacity. And ideally, if you run this test at the beginning of the life of the battery, this will be your baseline for training of the results. The next test is the performance test. So this is the test that is performed throughout the life of the battery. And again, the purpose of the objective of this test is to measure the percentage capacity of the battery. It's the main purpose of that test. You have to run this test with constant current or constant power. This is very important when setting up your load bank and selecting your load bank. You want that load bank to be able to provide a very stable current throughout the test, or rate of discharge, as per you said in the instrument when starting the test. The duration, now we want to test also as close as possible to the duty cycle. So when the designer of the battery or the substation, the designer of the substation selects a battery or specifies a battery, he needs that battery to be able to supply power for a certain time and under certain conditions. In this test, we are not simulating identically those conditions, but at least the whole duration of the test should be what the battery is expected to last or to provide power. And usually it's going to be similar to the acceptance test. How often to run the test? Well, the idea is to perform the test periodically every 25% of the life of the battery. So if it's a battery that it's designed for 20 years, you would be testing every 5 years. So really, you're not going to be taking too much out of the battery when you run a test. There's the idea that the capacity test is a destructive test, and one of the reasons is because you are using one of those cycles. Well, batteries are designed to provide many cycles, and by using 4 cycles or 5 cycles throughout the life of the battery, it's not going to kill the battery. Then the result if you want to use this test for trending purposes and compare to previous results, you need to prepare the battery. The battery has to be has to go through a preparation process that we'll discuss a little bit ahead, and that definitely will give you a good trending comparison, a good trending value. And if you just want to see if your maintenance procedures are working properly, if you are if your maintenance practices are being effective, and you want to see if the battery is deteriorating and not being influenced by the preparation, well, you run the test without any preparation of the battery. The third type of test is the service test. So in this test, we want, and that's why I have a different shape here in the infograph. In this test, you want to verify the ability of the battery to meet the specific application. So in this case, that's why I have this duty cycle diagram there. This is what I was talking about before. This is what the designer consider for the battery, and you want to simulate, you want to mimic with the load bank the operating conditions that were designed for the battery. And in this case, you can see that the very first minute the battery is going to be demanding or going to be delivering certain amount of current, and then from minute 1 to the minute 30 it's a different amount of current, and then from 30 to 60 higher current. So you want to mimic all of these, and the battery should go to the end of this duty cycle, in this case 180 minutes, and without reaching the minimum voltage. However, and you don't calculate the capacity. You could be at 90% capacity, you could be at 140% capacity. This test doesn't worry about that. This test just wants to see that you can demand all of these currents and all of this time from the battery without having any problem. Because it's a service test, you want to see the ability of the battery. You don't do any preparation on the battery, so you don't do maintenance, you don't do anything related to improve the condition of the response of the battery during the test. There are some couple of things that you might need to take care of just to avoid any kind of further damage on the battery, but really there's no preparation. And how often? Well, there's it's at the discretion of the owner or the operator of the battery. If you suspect that the battery might not be working very good because you had a certain event or there was a maintenance practice that was not correct, and you want to verify the operation of the unit, well, this would be the recommended tests to run. And again, you want to mimic this duty cycle. That's one of the difficulties of these tests, that you may not be able to get these as easily as you would think. So if this is the idea, you have to do a little bit of research and with the original system designs. If the test fails, then you have to review the sizing. Probably the battery was not properly sized, or the load in the substation has changed. That will be the very first question. If I would ask, if I see that there's a problem or the test didn't meet the duty cycle. Probably there were some loads added to the system that were not considered in this load profile, and then you need to resize the battery, or also check the maintenance practices, and probably equalizing the battery would help in solving the issue. Again, capacity is not measured during this test. You just run the test to see if it's able to, if the battery is able to supply the battery, the load. Then we have the last type of test, which is the modified performance test. And this test is a combination of the performance and the service test. So in this one, you want to verify the ability of the battery to meet the duty cycle. And in the end, you will end up getting the capacity value. Because it combines the two tests, the two type of tests, it will be and probably not so easy test to run. And you don't do any preparation. You just run the test without at the actual conditions of the battery. And there are actually three type of different modified performance tests. And depending on what you want to achieve, you want to select one of those types. We're not going to those details. It's probably not a so common test sometimes because the complications that it might represent. And in one of those kind of differences is that you need an aging factor for the battery. Usually, it kind of the standard value is 25% of aging at the end of the life of the battery. But it could be different, and you need that to calculate the minimum test duration of the battery. So it's probably not a common test. Going a little bit more about the testing schedule, when I talked about the performance test or the modified performance test, the idea is that you test every 25% of the life of the battery. Then, so here we can see that you have the acceptance test from production or at the factory, and it goes a little bit more farther than the initial installation. You could test at 6 months or even a year of installation of the battery. Then the very first performance test is completed ideally, or the recommendation is to do it at the second year of the life of the battery. At that point, you would, if you have an acceptance test, you would have a trending value or baseline value, and from that point you keep testing every 5 years. So in the end, for a 20-year-old battery, you test you test at the second year, and then 5 years later you test at the 7th year, 12th year, 17th year, and at the 17th year you are at 85% of the life of the battery. That's the kind of the expected life of the battery, or you have completed 85% of the life of the battery. If you run a test there and the battery is has a drop of 10% with the previous test, or the battery result is 85%, then you should test annually. So the last 3 years of the battery, you are actually testing every year. An exception to this is if you run the test at the 17th year and the battery still has 100% of capacity, then you don't see any aging there, you still have a lot of remaining life there, then you don't need to run every year. You run every 2 years for the reduce the maintenance or the testing frequency there. Once you run the test, you want to calculate the capacity. And as I mentioned before, there are two methods. There's the time-adjusted method, which is basically it's a division, or it's a ratio of the actual time of test. So we are running a test at a certain rate, and we are expecting with that rate the battery to last for a certain amount of time. And let's say that we are running to 10 hours, and the final result of the battery, or the final time that the battery reaches the end of discharge voltage, not at 10 hours, but it reaches at 8 hours. So in that case, our ratio would be 8, and in the numerator, 10 in the denominator. And if there's a temperature difference from the reference value, we use that temperature correction factor. And in this case, with a correction factor of 1, we would be getting an 80% capacity of the battery. That it's a simple calculation. Again, the problem is not a problem, but there's a lot of things that you need to consider before running the test and while running the test. So simple concept, but entails a lot of things there. The table for correction factor is provided by the IEEE standard, and this is the capacity calculation method recommended for acceptance, performance, and modified test of 1 hour or longer. Then the other test is probably not so common, It requires a correction factor because the rate has to be adjusted for uh, the aging of the battery, and you divide the rate used for the test over the published rating, and you also use a correction factor there. So this is recommended for acceptance and performance tests of less than 1 hour. So usually, for at least for the substation world, you don't have such short durations, and this test is or this calculation method is not as common. Correction factors are also provided by the standard, by the IEEE 450. So let's talk about the initial conditions. So what you need to do to be able to run the test properly. If we are talking about VLA batteries, then you need to equalize. You need to bring all the voltages of the battery to the same level, and ideally, and an equalized process, what it's going to do is to fully charge the battery. If this is a VRLA battery, or if you're running a service test, well, you don't do any equalize. This actually, the very first step is one of the ones that uses or represents more time in the preparation of the battery, because you need to equalize, and depending on the condition of the battery or the state of the charge and the charger and the type of battery, that equalized process might take 2 or 3 days. Once the equalized process has been completed, then the battery has to return to floating conditions, and the recommendation is that it should be floating for at least 72 hours. So even you don't go like in any transformer test that you go and take out the test instrument and run the test. You have to do this step ahead of time, and if something goes wrong during the test that you need to restart the test, it's not the same as with any other electrical equipment. In this case, you need to bring the battery back to equalized conditions or to recharge, fully charged condition, and then wait for those 72 hours again, and then you can continue the test. So a very important aspect to consider when getting prepared for a battery test. Next thing or next step is to do or check the battery connections. You're going to be demanding current from the battery, and you want the circuit to be in very good conditions. You want the straps to be with very low resistance. You don't want any terminal loose, or you don't want any contamination in the terminals that is going to be creating a hotspot for the current circuit, or a hotspot due to current circulation, and probably generating more damage to the battery. Then you record the floating conditions. You need to gather information about the float current, the float voltage of each cell. Even before running the test, you need to see what is the voltage condition of each cell. And this is basically a confirmation or a verification that the battery is equalized, that all of the voltages are at the same level. The battery is a system of 60 cells or whatever number of cells. You want all of the cells to have the same amount of energy at the beginning, and you want all the cells to be doing the same work as the other cells. So that's the purpose of equalizing and verifying those voltages. If it's a vented lead acid battery, you want to record the temperature of more or 10% of the cells or more. And this is because you need that information for the temperature correction. The temperature correction is based on the temperature at the beginning of the test. The batteries are not supposed to warm up or change temperature while they are discharging. There's definitely a temperature change when they are charging up, but not while discharging. So at the beginning of the test, you record that temperature, and you use that for the temperature compensation. If it is a VRLA battery, if it's a battery that has, it's a sealed battery, then you want to get the temperature from the negative post of that same 10% of cells, and then you calculate the average from there. Once you are done with the cell level, then you check the overall voltage at the terminals of the battery. It's a verification step. Then you take all of the precautions to avoid disturbances. So you're going to be demanding current from the battery. Are you disconnecting the battery from the load, or is the load going to still be connected to the battery? So you want to take any precautions to avoid any protection to operate because of low voltage on the battery, if you are leaving the load connected, or if you're bringing a backup system, this probably is the moment to connect the backup system. If you are switching to another battery, this would be the moment to do that switching. And then you disconnect the charger, and for this you follow the proper procedures to avoid, again, any problem, any disturbance in the system. And finally, you have the battery ready for testing. It's important to consider that the battery is going to be unavailable during the test if you're, of course, disconnecting it from the load. Even if you are running the test with the load connected, which is not very recommended, at the end of the test, when the battery has already given all the energy, if there's an event in the system, the battery is not going to have enough energy to for the switching operation in the substation. So you might be at a very difficult position there. So that's the reason for not running the test online. And after the test, you probably put the battery back on service. You turn on the charger. But if there's an event right after, in the very few hours after starting the recharge process, your battery is going to be with very low charge and might not be able to go through the events. So you need to consider all of these before running the test, and we are going to see some options for that. So again, to select the discharge rate, you need to define what type of test you're doing. If you're doing an acceptance or performance test, then you need to go to the manufacturer tables to get that rate of discharge according to the end of discharge that you want to run, and to the duration that you want to get. Now, one thing that you can notice in these tables is that they are not, there's no linear relationship between the durations. So once more, this is one more reason not to run a test with rates that do not match from test to test, because the results are not going to be comparable. And very important, going back to that concept or that idea that the battery testing, the load testing could be destructive, is this end of discharge voltage, the 1.75 value. That is definitely the point where you need to stop the test. You need to stop the test at that voltage. If you go below that voltage, then the test becomes destructive. Especially for the lead acid batteries, that is very critical. You don't want to go beyond that voltage. And it's the same concept as with an insulation test. An insulation test is insulation resistance test is not a destructive test. But if you run the test to a voltage that is higher than the nominal rating of the asset that you're testing, then you're going to definitely break down that insulation. So it's how you perform the test that will make it destructive. So capacity testing, if you go to this minimum voltage, should not affect your battery at all, and it's a safe test to practice. Going back to what discharge rate to select, if it is a service test, then you have to mimic the duty cycle, and again, the stopping point, if the battery doesn't reach the expected time, the stop point is going to be that minimum voltage dictated by the battery manufacturer. If you do modified performance test, you need to use both the duty cycle and the manufacturer tables. And again, for results trending, you need to use the same test rate for the life of the battery. So if you started the test, or the very first performance test was done at certain rate, the subsequent tests have to be done at the same rate to be able to compare. During the test, only one pause is accepted, and this pause cannot be longer than 6 minutes. Why would you have pauses during the test? Well, you could have an inadvertent trip of the test equipment, or disconnection of leads, or one of the cells might be reaching that end of discharge voltage, that 1.75, and you might need to bypass that cell to avoid that cell to become a load during the test. So if you are suspecting that that's going to happen, you need to be prepared to have to do that maneuver in those 6 minutes. And actually, it depends on the length of the test. The standard says that the test should not be the pause should not be longer than 10% of the expected duration, or 6 minutes, whatever is shorter. So if you have a test that is longer than 1 hour, your maximum pause time is 6 minutes. So you have to be very well prepared for this. And if you exceed that time, then the test is not going to be valid, because the battery will recover its voltage, and then the capacity will be not a reliable result. It's not going to be an accurate measurement. Also, during the test, you want to measure the voltages of the cells. The standard asks for at least 3 instances at the beginning, during the middle of the expected duration, at the middle of the expected duration, and at the end of the test. And this is to determine if there's a cell with problems. And this is actually the way that you can determine if you need to bypass a cell. Now, if you just do 3 times or 3 instances during the test, it's very little information. So the ideally and the recommendation from the standard is that you preferably measure these cell voltages throughout the test. So like we are showing here in the figure, you get a discharge curve for all of the cells. And then one more thing to consider during the test is that you don't want the temperature of the room to increase. Temperature affects the behavior of the battery, and if the temperature increases, then the battery will release the energy faster. And the opposite with the temperature, with lower temperature. If the temperature changes, or it's a low temperature, the battery will be releasing the energy slower, which will make the capacity to look higher. So you don't want the temperature to change during the test. And because capacity testing means releasing or dissipating a lot of energy in the form of heat, then if you are not dissipating that heat properly, and you are circulating that heat through the room, you might be affecting the temperature of the room. When to stop the test? I probably went ahead a little bit ahead of myself here in the slides. The end of discharge test, the end of discharge voltage is the minimum voltage dictated by the manufacturer times the number of cells. And discharging to lower voltages may cause damage to the cells. That's on going beyond the time, the expected time. Now, stopping the test, because at the moment that it reaches, so if we are expecting a 10-hour test, and we reach to the 10 hours and we stop the test immediately, well, we might be losing information from the test. We are not measuring the full capacity of the battery. We are just measuring the capacity to that point. So the battery might be at 130%, and we are just looking at 100%. So for the next test, if the battery still achieves 100%, but it is there was a change in capacity of 10% or 20%, we're not going to see it. So it's very important to measure the full capacity of the battery. So you could be missing this part of the information, and you don't know if it is going to be like this next time, or if it's going to be, or it was really like this. So measuring the full duration of the test down to that minimum voltage is really important for trending purposes. The analysis and replacement criteria. So I also mentioned a little bit of this before. If at the 85% of the service life, the battery delivers 100% of the capacity, if at that point the battery is still giving 100% of the capacity, it's like one of those persons that even has some aging already, but is in very good shape, and it's giving 100% capacity, then you don't need to test that frequently, and you just test every 2 years until the battery shows signs of degradation, and that degradation is defined as a capacity drop of 10% from a previous test. Then when to replace the battery? When the capacity reaches 80%, that's when we need to replace the battery. And this is from this point on, the curve of the change, or the capacity degradation, will be faster. There's a knee point that happens, and the capacity will drop very fast from that point. And once we get the 80% in a battery, we have like a year to replace the battery. So it's kind of the time that you have to go through the specification and purchasing process. So when we are running the test, what happens when we are running the test, and what things we need to consider? Well, the very first thing is go through all of that preparation, and we need to be sure that that preparation has been completed. And if we are taking some exceptions or making some exceptions, we need to document those and understand that those excepts are going to those exceptions are going to be there for when we do the analysis of the results. Then you need those discharge tables. I hear some background noise there. You need the discharge tables, you need a load bank, you need means to discharge the battery, and you also need a backup plan in regards to the batteries that you're going to use for supply, and what if something happens. And I'm discussing those things now. So the test connection. So this is how the test would look. You just need a load bank with the current cables. Now you want to consider also, before starting the test or for the preparation, you need to consider the length of those cables, and if you are and how are you going to handle the heat dissipation if you're going to have the load bank right there at the battery room. So you need to provide ventilation, or you need longer cables to have the test set or the load bank outside the room. You need to be prepared for bypassing any cell. And then if you are measuring the individual voltages from each cell, then this is how it will look, at least with the solution that we provide. And this is a more realistic picture where you see the load bank here, and then you have all of the voltage monitoring devices connected throughout the battery in a daisy chain style. If you need higher load, if you need higher current, because that's the characteristic of the battery, and the load bank needs to be increased, well, you could have multiple connections. You could have multiple load banks in parallel. And here, for the kind of preparation and the considerations for the field, is that at those terminals of the battery, the most positive and the most negative terminals of the battery, you should provide means to have good connections for those all of these cables to be connected. These parallel, or cables connected in parallel, are going to be here. So you need to provide good means there for the installation of that. So in some batteries, what they do is they provide, or they provision these they are ready for testing. So you just get there and you don't have to do any disconnection there. Then the backup plan. So again, the battery is unavailable during and after the test. You need to analyze and consider if you are going to have the load totally offline, or if the load is going to be supplied from the charger with the risk of an outage. You're just depending on the charger, or if you bring a temporary battery backup. And one more and very important thing to consider is during the test, you may want to have also testing performed on the charger, or you want to have the certainty that the charger is in good condition even before running the test. But because what if you finish the test, the battery is without any energy, and then your charger doesn't work? So that is a very, very important consideration before running the test. Examples of temporary battery backup could be something as simple as this, where you have regular car batteries connected right there at the substation. You bring them in a truck, you put them there in a pallet, and you at least in this case they already have some means to switch the load to this new battery. You can see the temporary installation. So once they have these and they do the switching here, now you can just go to the battery and run the test without any problem. So that's a very simple and nice solution that you can have there. Uh, or you can start building your own solution. And this is a very nice example I saw at a customer, that they have these little truck where they in the pickup bed they have these battery bank also with car batteries, and they have a charger inside of it, and they have their own load bank there. This is a panel where they can connect the system, the load of the substation, and it's a very nice solution, kind of homemade solution. And when I was preparing the presentation, the way the truck looks made me remember about this. Just a funny note that they're very similar solution. And well, you also have a temporary solution that it's more industrialized, more professional. This is a trailer, and when you open the back doors of the trailer, you see this inside. So it has all of the safety considerations. It has gas monitoring, hydrogen monitoring devices. It has actually two banks here, one of 130 and one of 48 volts. You have two separate chargers there. You have the distribution panels to connect, or switching devices to be able to connect the load from the substation here and then do the transfer. You have circuit breakers, and they also have the solution of the load bank. So they carry everything here, and this is their way to get prepared for the testing. So now we are at the point of the results. We are already discussed the different type of tests that we can run. We can discuss the different methods that we have available for the calculation. We also discussed the different aspects that you can face while running a test, and the different preparation that you need to go through. And finally, the results. So you want to analyze to see how your results are and how a report looks like. So no matter what you're using, the report has to be very well documented. You want to have in that report the site information, the battery information, the installation date, and battery temperature. And these are probably the last two pieces here are very critical: the installation date and battery temperature, because well, you need it for the correction factor, and you need to be sure that you are comparing apples to apples. And then installation date is critical to know if the result that we are getting is in line with the life of the battery. If we have a 5-year-old battery and we are just getting an 82% capacity, well, that is not good. So you want to know what is the installation date to be able to assess the result. Then you want to see in that report what is the capacity calculation method, if there's any correction factor, aging factor considered, and then of course the temperature correction, the voltage plot. The voltage plot is what you are mainly interested in a report. You want to see how the voltage behaved during the test. And you want to get all of these previous information, the float and open circuit voltages, individual cell voltages, and very critical, the pause duration. So here we see screenshots of different sections of a report. We can see the voltage, the measured capacity. We can see the corrected capacity, the percentage capacity, the calculated percentage capacity, the total duration of the test, and we can see here there were no pauses during the test. And also we can see the float voltage, the open total voltage once the charger was disconnected, then the start voltage and the end voltage at the once the test was completed. And this is the overall voltage behavior of the at the terminals of the battery. And this is a graph that shows each of the voltages of the cells with at the top of the bar you can see the float voltage, then you see a little white section. That means the end of that white section means the open circuit voltage, and the end of the green section means the final voltage after the completion of the test. And you can see that some cells went below that minimum voltage. That means that those cells probably need replacement, and probably they were left, they allowed them to go that low because they were almost at the end of the test. Then for the pauses, it's important to analyze that, to see if there were any pauses and that they were not longer than 6 minutes. And well, you would see in the result, if you don't have the time duration, if you see that there's this kind of interruption in the voltage curve and you see that the voltage recovers a little bit, that means that there was a pause. So you need to ask how long was the pause, because that might be deviating your results. The individual cell voltage, it's important because not all of the cells discharge equally, and the deeper they discharge, the faster the voltage will drop. So you want to see how each of the cells behave, and ideally, again, you want continuous measurement. And once you have the continuous measurement, you can have the information displayed in a bar graph, or you can have this type of graph that you have the discharge curve for each of the cells. So very easily here you can see that this cell, which I think it's cell number 20, I don't remember, it's probably not in a very good condition, and it reaches the lowest voltages faster than the other cells. So to summarize, the battery load testing is the only proven method to define the state of health of the battery and to determine the capacity. It's a very resource and time demanding test, and it involves a lot of careful preparation and logistics. It's not easy to repeat. If you made a mistake or if something goes wrong, you need to wait for a long time, and that's gonna be expensive. You have a lot of resource material. You have a lot of references there to ask or to look for information. And the analysis of the test goes beyond the percentage capacity. There's more information that you want to consider there. So the tools, what tools you can use for the test. So load bank, in our case, we have the Torkel 900, which is an instrument with a dynamic discharge technology that provides full power at all voltages. It can test from minimum voltage that it can go down is to 7.5, and maximum voltage that you can connect the instrument is 500. The dissipation capacity is 15 kilowatts, which gives you the ability to go to currents of up to 220 amps, depending on the voltage. And well, you can set also the test instrument, the discharge, to be constant power, constant resistance within those ranges that we have there. And you can do multiple configurations. So if you are using the regular load of the battery, you can use an external CT to be able to measure the total current so that the instrument can regulate. Or if you are using extra loads, it could be from a Megger or could be from any other type of load bank that you have. Well, if you use that external CT, then the Torkel can monitor the total current that is circulating through the battery, and the instrument will be able to regulate the current to a constant value that you require. And you can have multiple configurations for higher current levels. So if the 15 kilowatts that one single instrument can give you are not enough, then you can put more instruments in parallel to achieve the current levels that you need. And those extra loads, well, they are also different models depending on the voltage that you need to connect to and the different power requirements. For voltage monitoring, for individual or battery voltage monitoring, we have the VVMs, which are little boxes that are daisy chained through an Ethernet cable, and they can measure, or they can daisy chain up to 120 cells. Individually, they can measure up to 20 volts DC, and the maximum string that you can measure is 300 volts per string or per loop. And well, you can have two of those loops together. So in this case, you see that there's two sets of VVMs, and they can connect. This would be up to 240 cells, maximum 300 volts. And you can go also to systems up to 500 volts, and in this case there's a little accessory that needs to be used or to isolate those voltages from the battery to the instrument, but you can also go there. And using the same accessory, the optocoupler, you can still go a little bit higher. You can go to 600 volts systems without the Torkel, so connecting to a computer. In this case, what this means is that the VVMs are not only an accessory for the Torkel, they can act as a standalone instrument. And just a couple of more slides to finalize here, the optional connectors for VVM. So VVMs may sometimes, they have what it's called the Dolphin clip here, and you can connect. They come with the VVM, but if they are not easy to connect to the battery, where there are more options that you can use because they are banana connection, they can easily be extended. And you can also use an extension cable with an M8 ring connector that you can install permanently to the battery, and you can bring that extension cable with the corresponding adapter there. And also there's this battery pole bolt, which has a little hole at the top. It's already made like that, and it has a screw connection there. And then this adapter, banana adapter, on one end has the a screw connection. So you would bring those and we'll screw them here and connect the VVM the way it is looking here. So it's a very easy way to connect to a battery. And there are many other hardware configurations that you can ask us to see what solution we can provide or we can recommend. With these, well, I guess this is my last slide. This cartoon, it's made me remember the battery testing. The battery might be old, but it might have it be in good condition, and that is depending on the maintenance conditions and the maintenance practices. So it's not about the age, it's about the maintenance that you perform on the batteries. With this, I'm done, Michael, and I bring it back to you, turn it back to you so we can initiate the questions.
Awesome, thanks. So as said before, the presentation portion of this first segment has officially concluded. We now have a few minutes to answer as many of your questions as possible. If you do have any questions, please submit them now into the Q&A box on the right side of your screen. As a reminder, we do have one more segment after this Q&A, so don't disappear. We have some more good information to send your way. So our first question is going to be directed at Sankey, which is, what is float current?
So first of all, thank you guys for attending this webinar. So to start off by answering the first question, what is float current? A battery can store charge, but only for a certain time. So if you don't keep it charged, then it will tend to lose charge over time. So what's done is the battery would be connected to a charger, and the output of the charger would need to be set at a specific voltage depending on the battery to which it's connected. Now that voltage is called the float voltage, and the float voltage needs to be at a certain value. If it's set at a higher value, then what will happen is that will result in overcharging of the battery, which will lead to excessive current being drawn, which will lead to damage of the battery, lead to loss of capacity. On the other hand, if the voltage is set at a lower value, then that will result in undercharging of the battery, and over time the battery charge will drop. So both scenarios are not good for the battery. The output voltage of the charger needs to be set at the right voltage, which is the float voltage, and the current that the battery draws, the current that flows through the battery when the charger applies the float voltage, is called the float current. It's a small amount of DC current, which typically in milliamps, which flows through the battery, and through that current, it compensates for the open circuit losses. It should not be excessive. It should not be the current simply depends on the output voltage of the charger.
All right, thanks. So I'm going to send a question over to Andy, see if we got him back. We got you there, Andy?
I hope so.
Oh, hey, there you are. Okay, so next
All right.
question for you. What about the management of ion lithium batteries? Lead acid is being replaced by other technologies. Which standards cover lithium ion batteries?
Well, right now, the standards committees are sort of out on this. They're still working on the maintenance, so there is none that really covers the maintenance directly. You do have 1679.1, which is basically a guide to lithium-ion batteries. And typically, when you're dealing with lithium-ion batteries, they're going to have what's known as a BMS on them. They'll have a battery management system embedded in them, and they'll also have a battery monitoring system on it. Most of these lithium-ion applications are in energy storage, so they're seeing a cyclic application. So they're being discharged and recharged periodically, pretty much on a daily basis. So the battery monitoring systems are sort of monitoring a daily discharge and recharge. But the thing is with it is that it's not a complete discharge and it's not a complete recharge necessarily. It's always different. So is it giving you the whole picture? Most likely not. And you can do a discharge test on a lithium ion string. However, you do need to take some precautions in doing that, especially if you have parallel strings, because the battery monitoring systems will have cutoffs on them. So if the voltage gets too low, it'll cut off that string. So if you're pulling a load on the entire system, and one of those strings goes too low, it'll cut out. And then the full load will be put on the other strings. And what could happen is you could end up blowing a fuse on them. So you do want to be cautious if you're doing a discharge on a lithium ion parallel string. In that case, you probably want to set your cutoff limit very carefully.
All right, thank you.
You're welcome.
So our next question is going to be for Daniel. Daniel, what's the appropriate float time before a load acceptance test?
Hello, guys, and as Kat said, thank you for attending. So, and this one goes hand in hand with that section that Sanket talked about, right? The float current. So again, this current being the result of the float voltage that the charger is applying to keep the battery charged. Once we reach at 100% charge on the battery, we should start counting 72 hours to be for the battery to be ready to run not only discharge or load testing, but other measurements like impedance. And this is to allow the battery to stabilize after the charging process. So again, after you reach 100% charge, that's when you start counting the 72-hour period for the battery to be ready for testing.
All right, thanks, Daniel. Sanket, does load test reduce the lifespan of the battery? Is a discharge test considered destructive testing?
So Volney did touch upon this during his presentation. There is this misconception that the load test kind of reduces the lifespan of the battery, but if you think about it, a battery is manufactured to last for 100 discharge cycles at least. So if you are doing, let's say, for a battery with a service life of 20 years, let's say you do a discharge test every 2 years, you end up doing 10 discharge cycles in that case. And you're not doing, you're not going too deep on the discharge either. So I would say that it does not reduce the lifespan. Taking a few cycles out of the life of the battery is not a big deal. And it's not a destructive test because you're not going too deep on the discharge.
All right, thanks, Sanket. Daniel, next question's for you. What kind of equipment or tools do you need for this type of testing?
Okay, good question. Apart from obviously the instruments that Bonnie touched upon, right? The discharge unit, in our case, the topple, and the individual cell monitors, the DVMs. Obviously, when you talk about the tools, everything you need to, for example, jump out a cell, right? Bonnie did cover this on his presentation. You need to be ready to jump out any cell that is necessary that you identify with the DVMs to be weak before the end of the test. So you have to have the appropriate connections, insulated tools, and obviously that equipment list cannot be 100% complete without talking about the safety side of things, right? The individuals involved with the test have to have the proper PPE and also a wash station. And even we can even talk about ventilation in the battery room. So obviously PPE, all the tools necessary to do the proper connections for both the instrument, the VVMs, and in case of dumping out cells, and obviously the instruments themselves.
All right, thanks. We have time for one more in this session because we're running really short on time. I'm going to send it over to Sanket. If batteries are load tested and then shipped to a location and sit for 6 months without trickle charge, when do you retest those batteries?
So going back to again what I mentioned about the charge on the battery, a battery is capable of storing charge, but over time the charge drops if it's not being continuously charged. So if a battery is going to sit there for 6 months without any trickle charge, that means that the charge on the battery is going down. So when you reinstall the battery, what needs to be done is it needs to be recharged first of all, and then needs to be kept on float condition for the recommended period of time as per the guides, depending on the type of battery that it is. And after that, it is recommended to run another discharge test on the battery simply because it's been sitting there without any charge for 6 months. So to find out if there has been any permanent loss of charge on the battery, you want to do another discharge test and find out the actual capacity of the battery.
All right, thanks a lot. So as you guys might have guessed, we are running a little bit low on time, and we have scores of great questions that we're going to answer offline in the next coming weeks with our panelists and our presenters taking the ones that they need to answer offline with you guys. So keep an eye out on your inboxes for those, because we don't want to be skipping over some of these questions, because you guys have very valid ones to bring up. We just don't have the time to go through all 110 of them. With that, we're going to jump over to our second presentation, which we've moved over to Andy Sagel. Andy, I'm going to send control over to you real quick. You with us still, Andy?
I'm with you.
Cool. All right.
All right, so that actually worked. Good.
Hey, progress. All right, so we'll jump in to your presentation, and Wheel of Kosher.
Okay, you can see everything, huh?
Yep. Go for
All
it.
right. Modern technology. There you go. And what we're going to do here is we're going to be covering stationary battery maintenance. Okay. What we're going to do here is we're going to cover different battery types, their applications, their failure modes, and the different battery testing methods. And we're going to delve into ohmic testing and some of the pitfalls you can get to. Then we're going to look at how you actually analyze that data to make determinations. And then we'll take a look at some of the units like the byte units, power dB, and we'll cover some maintenance schedules. Now let's go to the battery types. When we talk about the battery types, the first thing we're going to hear about is you have primary cells and secondary cells. Primary cells are the ones we're all familiar with. They're our Duracell or Energizer. When they die, we throw them out and replace them. Secondary cells are our rechargeable cells. These are the batteries that we're going to be talking about here. The secondary cells, by the way, they're called secondary cells because a primary cell, as soon as it's built, has a charge. Rechargeable batteries are secondary cells. When they're built, they have no charge. They require a secondary operation to charge them up, hence secondary cells. Now, out of the secondary cells, we have lead acid, NiCad, and lithium ion that we're going to be talking about in this presentation. The lead acid cells, we can break them down into cyclic batteries and standby batteries. Cyclic batteries basically being the ones used in forklifts and all different types of applications where they're continuously cycling. And our standby batteries, these are the ones that we're using in the substations, telecoms, and data centers, and going to be more of what we're going to be focusing on here. Now, lead acid batteries, they also come in different types. You have VLA or flooded cells, and you also have VRLA, valve regulated lead acid or sealed cells, sometimes commonly referred to as maintenance free. Now, the flooded cells, these are the ones that have a lot of electrolyte in them, and we can add water as the electrolyte goes down. There are several big pros to flooded cells. One, they have some of the longest lifespans. They can have a 20 to 25-year lifespan on them. Also, they fail on what's referred to as the shorted mode, which means that when they fail, they're not necessarily shorted, but current still can pass through them. So in critical applications, you can use series strings, and if one fails, you're still going to get current through. The con is it vents hydrogen gas. Now, when we hear about this, we always think of the Hindenburg. Well, hydrogen is the lightest gas in the periodic table, so it not only rises very quickly, but it disperses very quickly. So the real thing we want to make sure of is that when we use these, we have some sort of ventilation in the room. That's really all we need is some good ventilation. And it would be best to have a hydrogen detector as well to be on the safe side. Sealed cells are valve-regulated lead acid batteries, also referred to as maintenance-free, which ironically, they sort of require the most maintenance. Pro is they're low cost. They're inexpensive. The con is that they fail in what's referred to as the open mode. Now, it doesn't mean they're open, but it means the impedance has gone up so much that current does not readily pass through them. This means that when these are used in critical applications, you really want parallel strings, so that if one fails, you can still get current through the parallel string. In addition, these have your sort of limited lifespans. Typically, a well-maintained VRLA battery will last you about 5 to 8 years at tops. If they're not well-maintained, you can have them fail in 2 years, or I've seen them fail even sooner than that. Another con is these do require a temperature-controlled environment, and as we get into failure modes, you'll see why. NiCad batteries. NiCad batteries are a different animal. They do not have an acidic electrolyte. They have an alkaline electrolyte to them, which gives them a different discharge profile. If you ever use them, you'll notice that when you're discharging them, the voltage holds pretty steady throughout most of the discharge and then drops really quickly at the end. Pro, they do have a better temperature performance than lead acid. Okay. Now, that doesn't mean that temperature doesn't affect it. It does. Okay, but they do handle higher temperatures somewhat better. Also, they also have long lifespans. You can get 10 to 20 years out of the flooded versions of the NiCad batteries. Con, They are prone to dendrite buildup and can fail suddenly. And again, we'll cover that a little bit more in the failure section. Lithium-ion batteries. Lithium-ion batteries is actually a family of batteries. There's tremendous different types of chemistries that are out there. And here we're seeing just some of them. And they are designed for different applications. So when you're going to use these, you really want to try to look at the chemistry that's going to best suit your application. Okay. Now let's get into those applications. When we look at batteries, they're not created equally. Different batteries are designed for different applications. And if you use the wrong one, you're going to have some issues. Number one, when you're dealing with lead acid batteries, the more plate surface area means the more charge you have, the more capacity the battery will have. So the larger the battery, the more plate surface area you're going to have. Now, in cyclic applications where you're discharging and recharging all the time, you're generating a lot of heat. So you want thicker plates. The thicker plates deal with the heating better. So that's what you'll see in cyclic batteries, thicker plates. And when you want higher capacity, you're going to need more plate surface area. They also come in different chemistries. You have lead antimony batteries, lead calcium batteries. You also have lead selenium batteries. Now, lead antimony batteries, they are better in your cyclic applications because they handle heat better. So they can handle the many charge and discharge cycles you see. However, lead antimony batteries are not ideal in standby applications. This is because when they're left in float for extended periods of time, the antimony can leach into the electrolyte. It's called antimony poisoning. And then what you'll see is it will start drawing more flow current. You'll see the flow current going up over time. And that is a sign of antimony poisoning in these types of batteries. Lead calcium batteries, on the other hand, these are much better for float applications because they don't suffer from antimony poisoning and they draw lower float currents in general. Lead calcium, though, is not exceptionally good in cyclic applications. This is because it doesn't deal with the heating effects as well. So you'll notice with these batteries, they have a lower number of cycles in their life. And again, when we talk about cyclic batteries, we're going to be looking at lead antimony designs, and we're going to be looking at thicker plates. They withstand corrosion better. Now, there's another type called SLI batteries, starting, lighting, and ignition batteries. These are our car batteries, our motor startup batteries. These batteries are unique, is they are designed differently. They have many, many thin plates in them. This is to be able to provide a lot of capacity. Because what do you do when you start a car? You have to draw a lot of current for a very short period of time. So these have to be able to supply that. However, they also can't be discharged very low because there's very thin plates and the separators between them are very thin. They're packed in under pressure. So when you have these where they discharge too much, you can get dendrite buildups. And I'm going to go again. We'll get into that a little bit more when I get into the actual failure modes. But you'll notice that these type of batteries, as soon as you start a car, what happens? The alternator recharges the battery. So starting, lighting, ignition batteries should never be used for anything outside that application. Stationary batteries, these are typically our lead calcium designs or lead selenium, which lead selenium is actually a lead antimony battery just with a very small antimony content in it. And these are good for long periods on float. And they're not very good for the cyclic applications. And these are typically the ones we'll see in substation, telecoms, data centers. Our NiCad batteries, where are we going to use these? Well, one place we can use these is where we have limited space because they do have a higher energy density. And they do tolerate high heats better. So if you're in uncontrolled environments, you may be wanting to use these. That's one of their key applications for them. Now, they are more expensive as well. Okay. Prismatic lithium-ion batteries. Now, these are a little bit of a different animal here. Instead of having larger plates to get higher capacity, what these do is they have a bunch of small cells inside them. These cells are in series parallel configuration, so they can be designed for different voltages and different capacities. And if you notice in the image, there is a circuit board inside there. That is because they require a battery management system internal to the pack. This pack it ensures that all the cells remain balanced. Okay, it's critical that they remain balanced, and these are also going to monitor how fast they can charge and discharge, because this is where you can get into plating issues that occur. And again, I'll talk about this more in failure modes. And these types of batteries are commonly used in energy storage applications, such as solar farms and wind farms and things of that nature. They're not typically used in standby applications. Okay. And with failure modes, let's get into these a little bit. Positive grid corrosion. This is a failure mode in lead acid battery. So what happens is the lead alloy turns into a lead oxide. When this happens, those oxide crystals are larger, so the plates actually grow. So if you ever look at the bottom of a flooded battery that has a clear case, you'll notice there's a gap there. That's to allow for plate growth. If the plates grow too much, you'll even see the battery start to bulge. And by the way, if you see that, then it's time to replace that battery. There's no question about it. Testing is done at that point, and you just replace it. Now, as temperature increases, chemical reaction rates increase. So your corrosion rate increases. So heat is the enemy of our battery. And so this can be, corrosion can be accelerated by adding heat, and you can add heat by overcharging, excessive cycling, excessive temperature. So all these things will reduce the lifespan of the battery. And as the lead turns into lead oxide, you're losing active surface area on the plates. So what ends up happening is the internal impedance of the battery increases. So as it corrodes, the impedance increases. You also have sulfation that occurs. Sulfation occurs as a battery is discharged. When the battery discharges, the active plate material turns into a lead sulfate. When you recharge it, it reverses the process. Now, when the active material turns to a lead sulfate, again, you're losing active surface area. So your internal impedance goes up as your capacity goes down. And the problem you can run into here is what happens if you're undercharging the battery? If the battery is being undercharged, then it's partially sulfated. And the longer it remains that way, the harder the sulfation crystals get. Now, you may hear of times of doing what's called an equalization charge or a boost charge. These are where you raise up the voltage on the battery to a higher level. What that is intended to do is to break down sulfation crystals. That's what the intent of that is. And as they break down, you regain some capacity. However, the longer they remain sulfated, the harder it is to reverse them. If the plates remain sulfated or partially sulfated for a long enough period of time, equalization or the boost charge will not work. It's actually going to take a chemical process to do it. So this is why we want to verify that we're not undercharging on any of the cells in our string. Shorts. There's basically two types of shorts you can deal with: hard shorts and soft shorts. Hard shorts are pretty much due to paste lumps in manufacturing occur, and these you're going to see pretty quick. You're going to put them in, and days later, a week later, the battery's going to fail due to a paste lump going through the separator and shorting a plate out. Now, soft shorts, these are caused by deep discharges. When you over discharge a battery, what happens is that as the battery discharges, the pH level approaches 1.0. That's the pH of water. It's called watering the battery. At that point, the lead on the plates will begin to dissolve into the electrolyte and get trapped in the separators. This creates tons of micro shorts in the battery. Okay. Now, I mentioned about the car battery before, the SLI battery. if you ever had a car battery that died, what do? You jump it, you recharge it, and you go on with your life. Then you find it died again. You do the same thing, and it dies faster and faster. The reason that's happening is because every time it drops too low, you're getting lead going into the electrolyte, getting trapped in the separators, creating microshorts. Every time you do that, you're increasing the self-discharge rate of the battery. So it just discharges faster and faster as it's sitting there. So eventually, and that also increases the heat in it. So eventually you can end up with a safety issue. We often hear every time a lithium-ion battery catches on fire, it makes the news. But the battery that catches on fire the most are car batteries, because people don't replace them after this. And they just keep using them until eventually you have that failure. So the best thing you do, if you have a car battery die, just replace it. Dry out or loss of compression. This affects VRLA batteries, or the maintenance-free batteries. Now, in maintenance-free batteries or sealed batteries, you can't add electrolyte, but as they discharge, they still create hydrogen and oxygen. But in these batteries, that gets routed over to the negative plate, where it steals electrons off of it to reform your electrolyte, to reform your water in the electrolyte. However, no chemical reaction is 100% perfect. So you do have dry out over time. They do slowly dry out. Now, this can be accelerated due to heat, overcycling, overcharging, high ambient temperatures. And as that dry out increases, it draws more flow current, which increases the heat in the battery, which causes the dry out to happen quicker. Okay, this is one of the reasons you want them in temperature-controlled environments when you're dealing with sealed lead-acid batteries or VRLA. Now, as they dry out, let's think about this. What happens is that they're going to draw more flow current, which means they're going to run hotter, which means they're going to dry out faster, which means they're going to draw more flow current, which means they're going to run hotter and dry. Now, if this becomes a self-sustaining reaction, that's where you get what's called a thermal runaway. When that occurs, the battery is going to fail catastrophically. Okay. The best thing you do if you're using VRLA batteries is to be sure you're using a temperature-compensated charger that monitors the flow current so that it doesn't get excessive. And during your testing maintenance, you should always be monitoring float current to see if you start seeing it rising over time. I don't like the term thermal runaway because it makes it sound like it happens instantly. Really, it should be called thermal walkaway, because if you're monitoring your float current, you will pick this up. Negative plate depolarization. This again affects VRLA batteries or sealed batteries. This is due to the recombination effect. This happens when they are charged too quickly. When they get charged too quickly, the negative plate can become depolarized and will not hold a full charge anymore. And what you'll end up basically seeing in this is that when you do an impedance test on the battery, you're going to see the impedance will increase in the battery. Now, when you're doing this type of, when you're looking at a battery, you have a electrolyte and a plate. It's a liquid meeting a solid. Whenever you have that, you have what's called a double layer capacitor. And it's a capacitive property that this failure mode affects, so that this can only be picked up through AC style testing. If you're doing a DC style test on the battery, a DC ohmic test will not pick up this failure mode. Only the AC mode will work on this one. And this again affects VRLA batteries. Separator deterioration. This affects NiCad batteries. This is how typically a well-maintained NiCad battery will fail due to this. The separator will eventually break down and the plates will short out. And that's the typical failure mode in a NiCad battery. Now, you also can have carbonation in them. And again, part of the aging process. As I mentioned, they have an alkaline electrolyte. The potassium hydroxide will enter into a chemical reaction with the carbon dioxide in the atmosphere that forms a potassium carbonate. This has a higher resistance. So what will happen is the battery won't pass as much current. So it looks like its capacity is being diminished. So this you'll see as a rise in impedance. And this can actually be reversed by exchanging the electrolyte in the battery. Okay. However, in NiCad batteries, they use cadmium. And cadmium is naturally prone to dendrite formations. This is a picture from NASA showing the dendrite formation on a piece of cadmium. Now, if that dendrite pierces the separator, it'll form a short. And you'll see this because the impedance will drop and the voltage will drop. Now, at times, what you'll see this is it'll look like your battery's lost capacity and voltage. And you may talk to a battery manufacturer and they may say, well, what you want to do is bring the battery down to 0 volts, which is NiCad's the only one you can actually bring down that low. Just be sure you don't ever reverse the voltage. And bring it all the way back up. And they call it reconditioning the battery. And what you're actually doing when you do that is during that recharge cycle, you're creating a tremendous amount of heat in the battery. When you do that, you're burning out the dendrites. However, they've already pierced through the separator, and that damage is permanent. So you will always have that. So if this starts happening, it's going to continue to happen. Okay. Lithium-ion batteries. Their failure mode is actually what we refer to as SEI layer buildup. It's the solid electrolyte interface. And as these batteries age, this layer builds up. And you may hear it also referred to as capacitive fading, because over time, these lithium-ion batteries need to be derated because of this. As the SEI layer gets thicker, the resistance or the impedance of the battery increases. And as that increases, we'll see that in an impedance test. You'll actually see the value increase. And right here, these are actually impedance values. These are shown that how the capacity of a lithium-ion battery directly correlates to impedance. So actually, the manufacturers are doing these types of tests as well as all the researchers as well, doing these type of tests on lithium-ion. Now, another thing that can happen with lithium-ion is that you can get plating that occurs. Plating will occur if you're charging at too rapidly of a rate. When they charge, lithium ions have to intercalate into the plate. They can only do this at a maximum rate. If you exceed that rate, the lithium will start plating up, creating dendrites. Now, as the temperature drops and it gets colder, chemical reactions slow down. So the plate intercalates at a slower rate, so that the charge rate has to slow down. Now, this is one of the functions of the BMS system, that to control the charge and discharge rates of your lithium-ion batteries, so they don't you don't have these runaway conditions that can cause plating. Loose connections. This is probably the most common thing you're going to see, and this applies to every type of battery. And this refers to your intercell connections or straps. And if you think about it, the strap is like a little resistor, a very tiny resistor. It gets a voltage drop across it. That voltage drop, if you have a bad connection, what happens? This resistance goes up, the voltage drop increases. Across your string, as it happens, it builds up. That means the batteries at the end of the string can have a lower voltage across than the ones at the beginning. That means, in lead acid, that means they're not going to fully charge, which means they're partially sulfated. If they remain that way, you could lose capacity permanently. So straps are very critical to test. We always want to test straps. Now let's go to some testing methods. One thing about testing is no single test will tell you the whole story. You want to actually have a battery maintenance routine in place, and that's regardless of the type of battery that you have. Visual inspection is always a very important part of it. Checking electrolyte levels, checking the batteries, see if there's any cracks or deformations or leaks. And if you see that, you replace them. Checking for corrosion and verifying ground faults or necessities. Float voltage. The float voltage we always want to check. The float voltage is typically going to be dictated by the battery's data sheet. It's always important to get that and to check these values. And on some batteries, you'll notice that the float voltage will be derated based upon the temperature that they're used in. So it's very critical. If you have a low float voltage, you can be sulfating the plates. A high float voltage, and you're heating up the plates, accelerating corrosion. Float current. This we also want to always monitor, and you can test it anywhere in the string. And we want to see, is it slowly rising over time? If it is, that's a sign that you could have a problem and you need to deal with that. If you see it suddenly go up, you may find out you have a ground fault, or the batteries just aren't fully charged. And they need to, and if they're not fully charged, obviously they're going to draw a lot more current. Ripple current. Now, float current is your DC current. Ripple current is your AC current. And typically, now the AC current can cause heating effects in the batteries, and heat is not good for them. So IEEE recommends that you don't exceed 5 amps of ripple for every 100 amp hours of capacity. The other thing that's important too is your frequency of your ripple, especially when it comes to lithium-ion batteries. Now, low frequency ripple is not shown much, doesn't have much of an impact on lithium-ion batteries, provided that you're not raising and lowering the float voltage because of the ripple. However, medium frequency ripple from 10 kilohertz to 15 kilohertz in that range, that has been shown to actually damage the BMS systems in some lithium-ion batteries. So that is something you might want to watch out for when you're dealing with lithium-ion. Because if the BMS system gets damaged, you will lose the battery rapidly. Specific gravity, this is where we're going to be looking at the pH of the electrolyte as compared to that of water. And this is going to really tell us if the battery is fully charged. Really, to be honest with you, the only type of battery you really need to do this type of test on is flooded lead antimony batteries, because of the fact they can suffer from antimony poisoning, and specific gravity testing can pick that up. But in general, the other types of batteries, if you're doing float current, you really don't have to do specific gravity. It's sort of redundant. Temperature. We have what's called the Arrhenius effect. Now, I've been talking about how temperature is the enemy of batteries, and that's basically because temperature, as it goes up, accelerates chemical reactions. And the general rule of thumb, regardless of chemistry, is as soon as you increase the temperature by 10 degrees Celsius, you're going to half the life of the battery. That's a general rule across the board. Discharge testing. This is the only test that will actually tell you the actual capacity of the battery, and it should be done on a quarterly basis, as Volney had already discussed. Ohmic testing. Now, ohmic testing, there's 3 types of ohmic testing: impedance, conductance, and resistance. And as the battery ages, the chemistry changes. And as this happens, it causes resistance changes in the battery. So what we'll see is we'll see the ohmic values change. Typically, as the battery ages, the ohmic values go up. Intercell resistance, as I said, this is a very important test to do. And we want to make sure when we take these tests, we're taking those tests at the posts. And the reason being is that the terminal resistance. If you just take it across the strap, you're not taking into account the impedance or the resistance of the post to the strap. So if you take it on the post, then you're all inclusive. You're getting all the measurements there. Now, ohmic testing. There's 3 different types: resistance, conductance, and impedance. Resistive style ohmic testing, what it does is it draws a lot of current from the battery and looks at the voltage drop across it to calculate the resistance. The pro to this is that it tests with high current, so it's good on large batteries. The con is that it discharges the battery, so it's not a repeatable test. If you slip or have to retake a measurement, you do have to make sure that the battery is recharged. The other thing is that a battery is not a resistor. It does have a capacitive quality due to the double layer effect. So any changes in that double layer will not be picked up in this type of testing. And that's very common with VRLA batteries. Conductance testing. Conductance is the reciprocal resistance. However, they're actually doing admittance. They are doing an AC test, but what they're sending in is a compound signal that is very low level. And the pro to this is it will detect capacitive changes in batteries, and it doesn't pull back current from the battery. The con is it's very low test current. And you're also operating at 1 kilohertz, and that's right in the noise range. In addition, because of the compound signal they use, they have to use an algorithm to try to determine the impedance of the battery or the conductance of the battery. And I've gotten complaints in the field that this is not always representative of it. So, take that for what it's worth. Impedance testing, that's a 4-lead Kelvin measurement. 2 leads push AC current through the batteries, and 2 leads measure the AC voltage across the battery. And therefore, the impedance is then calculated. Pro, it will detect capacitive changes. It doesn't pull current from the battery, and it doesn't use an algorithm. It's a direct measurement. Note that these type of test sets can either work on low current or high current, so you want to make sure you pick the right one for your battery string. And they can also operate at various frequencies. So the higher the frequency, the more in the noise range you are. You really want to go with lower frequencies. And if you're going to be doing testing on lithium ion, you have to use low frequencies in order to do the testing. Now, keep in mind, ohmic testing is not an absolute test. It doesn't say this battery is good and that one's bad. What it tells you is that I have a problem. When I see that impedance go up 30 or 50%, that's a flag. That says I have an issue and I need to troubleshoot it. It very could well be that the reason I'm having a problem is because I have strap issues, and they may need to be corrected. So when I perform an ohmic test, there's a few rules I have to follow. One, most important, the string has to be fully charged. Ohmic test, as I said, is not an absolute test. I'm comparing the results I get today to previous ones. So if the batteries aren't fully charged, the plates are partially sulfated, which means they have a higher impedance. So now I no longer have a correlation to previous tests. So you always, no matter what type of ohmic test or what type of test you're doing, you want the batteries fully charged. And you want to use the same make and model instrument. If you change the make and model, you do want to establish a new reference or new baseline. It's not difficult to do, but you do need to do that. You want to use the same type of probes, as obviously if you use different probes, you may change the measurements depending on the type of unit you're using. And you want to make sure you take the measurements at the same point, which posts are the most preferable. So if you are doing ohmic testing, you should have a procedure on it to make sure that people follow the same methodology when they do the testing. Pitfalls you can run into. One, batteries have a low impedance. The bigger the cell, the bigger the capacity, the lower the impedance. So if you get a battery tester that's testing with 100 milliamps and the cell is 100 milliohms, the voltage drop is only going to be 10 millivolts. And in this case, if you're on a noisy system like in a UPS, it's very likely that signal is going to get swamped. And so you're going to actually be measuring noise and not the actual signal. If you have something that's putting out 10 amps, then the voltage drop is 1 volt, so 100 times higher. So this can help avoid those false results. Also, if you're dealing with straps, think about it. You don't want to try to test a micro-ohm measurement using 100 milliamps. You're going to have no resolution, and you're going to see no changes in those straps. They're always going to look good, even when they're not. Now, when you test a strap, you do want to use some more current. So some people will try to use a low resistance ohm meter to do this. Now, those test with a DC current. Now, keep in mind that you already have DC current going through the string. So if you're going to use that, you have to take the measurement in both directions and take the average of it to get a accurate reading there. And some low resistance ohmmeters do have this function built in. The other thing about them now, if you use duplex leads to do this type of measurement, a duplex lead is a type of lead that has both the current and voltage pin on the same lead at a set distance apart. If you're doing that, the measurement is going to be relative, no matter what type of instrument you use. It will be a relative measurement because you do not have a uniform current density yet because the pins are too close to one another. If I get another set of leads that have the pins at a further distance, I'm going to get a different reading. So what I want to do is I want to see how much they change from my previous reading. Now, if you have a system that injects current through the whole string, you have a uniform current density, so the readings will be absolute at that point. Stainless steel hardware. When you're using batteries like NiCad batteries, you may find that you can't get to the posts with the way they're designed. You have to go through the hardware, and if the hardware is stainless steel, you cannot use duplex leads. The reason being is one pin's injecting current, the other's looking at the voltage. Well, you're injecting current through stainless steel, which has a higher impedance, and it could have a higher impedance in the battery, which means you're actually measuring the resistance of the hardware and not the battery. So in these type of cases, you want to inject the test current through the string. When you do this, it doesn't go through the hardware, so that you don't get that voltage drop across it, and you can actually get real measurements. Parallel strings. When I deal with the series strings and I inject current to do an ohmic test, notice I only have one path for it to go through the cell that's being tested. If I have parallel strings, I now have another path for it to go. IEEE will recommend that you segment the strings. And in fact, if you have a bad battery and you have parallel strings and you're testing like this, basically every value on every battery is going to change. You're not going to be able to find the bad cell without segmenting, unless you measure what's called escape current. Escape current looks at the test current not only going through the total system, but also the current going through the parallel path. It can then subtract that from the total and determine the current going through the actual battery under test. So you get the proper value for it, and you get repeatable results, and you do not have to segment the strings in order to do the testing or any troubleshooting to find a bad battery. Now, what do we do with all the data once we get it? The ohmic data? Okay. The first thing we want to look at is the voltage levels of those batteries. Those should be within about 1%, and the data sheets will really call that out. They should be relatively tight. Now, this is an actual customer's data. This is real data we're looking at here, and you can see this is a fairly unbalanced string here. And basically, in this case, the problem wasn't the batteries. The problems were the straps. The straps were corroded. He had too many voltage drops across them, so we had to take them apart. They had to be cleaned up, and the whole system needed to have an equalized charge done to equalize all the batteries. When we look at impedance, there's three ways we want to look at that. We want to look at the percent variation, which compares each battery's impedance to the string average impedance. So what's that going to point out to us? Well, it's going to point out to us where we have potentially problem cells. If we see that value of one battery increase 30 or 50% above the string average, that's a flag. That says we want to investigate. And that battery could be going bad, or again, it could be a strap issue, or we could have very unbalanced voltages. But all of these can lead to these. You may find you actually have a bad battery, but you do want to do the due diligence of the troubleshooting. Now, let's say you test the battery string and all the batteries are within, their impedances are within 5% of each other. It looks phenomenal. But the whole string is aged from the time you put it in. Well, percent variation is not going to show that to you. That's why you also want to look at percent deviation. That's how much the battery its impedance has changed since it was put into the string, since the string was installed. And that's comparing it to the baseline value. The baseline value is basically the average of the string the first time you've done the test on it, so that we can see how much that's changed. If we see that multiple batteries in the string have changed 50 to 100% from the baseline value, that's a flag. That says we really have to do a discharge test on these batteries because they may no longer be any good. And finally, there's the trending of the ohmic value to look at the changes from one test to another. So I look at my cells. Every time I do an impedance test on a battery, I have values on each cell. Now I can trend each cell's value and see how its impedance is rising. Now, what does that do for me? Well, one, it's going to sort of let me know how to forecast when I'm going to need a new string. And two, if I have batteries that are supposed to last me 20 years and I see the impedance really rising up after 5 on them, and it's really going at that rate, I really should see, I might have a maintenance issue, maybe it's a heat issue, but there's something to investigate there, and your batteries won't last as long as you think they're going to. And straps. Basically, IEEE will tell you if your straps change by 20%, take them apart, clean them, and put them back together. Okay, that's their basic standard on there. And straps are probably the most common thing that fail because they are subject to vibration, heating and cooling effects, moisture, all these things. So these are critical to actually test. And let's go through some of the units we have here. The Byte 2P. This will measure cell voltage, cell impedance, ripple current, and strap resistance. It tests with 10 amps of current that's injected through the entire string. So it verifies the string continuity. This, because it injects through the string, also operates with stainless steel hardware. And it has a built-in printer in it because some locations have IT restrictions where they don't like you to put peripherals on your computer or have to use software. So we do print it out there. On there, and there's also optional extenders for tight locations and an optional barcode scanner, so you literally don't have to do any programming. You just walk up, scan the battery string, and start testing. Now, the way this works is it's a two-piece system. You have a transmitter and a receiver. The transmitter is connected across the entire battery string. It can be connected across up to 275 volts. DC. If your string is higher than that, you just connect it across pieces of the string that are under that, and you don't have to segment the string. You just connect it across pieces if you have a much higher voltage string. Now, what will happen is before you start testing, the receiver is going to ask you to put a current clamp on, and it's going to show you the ripple current going through the battery string. And then you'll get the 10 amps injected through the string. And then basically, we're just going to take the receiver and simply put it across the battery, then a strap, then a battery. We literally just go walking right through the cell, right through the string. We're good for batteries up to 25 volts DC. And you just go through each one, and it's a very fast test. One pass through the string gives you all the data you need, all the data to do the analysis. And typically, each measurement takes about 3 to 5 seconds, depending on the measurement and the type of battery. When you're done, you literally can print out the data on the spot. You'll get a bar chart so you can easily see where you have potential problems. And of course, you can transfer the data to the software PowerDB for further analysis if you like. The Byte 3 will measure cell voltage, cell impedance, ripple current, float current, strap resistance. It tests with 500 milliamps of current. It's lower current. It's not meant for big flooded cells. Okay, this is meant for your smaller cells. And it will do straps at 500 milliamps, but it's a relative measurement. You have to compare it to the previous measurements. Okay. And now with this system, this will allow you to measure escape current, so you never have to segment parallel strings. So it's ideal for parallel string operation. It also has optional extension leads for tight locations, and it has a graphic display so you can view data right on there. And it also has a built-in spectrum analyzer, which is ideal when you're doing things like UPSs, which are highly noisy. The byte 3 is a one-piece unit. It injects current through each individual cell. So you don't want to use this if you have stainless steel, okay? And it will measure lithium-ion battery impedance. The byte 3, they both operate off low frequency, so that's really no issue. The byte 3 will auto-identify if it's on a cell or a strap, so you really don't have any programming to do to this. You literally put it on a cell, it goes at cell 1 and measures it. And then you go to a strap, it says that's a strap, that's strap 1A. Go to another strap, oh, that's a strap, that's strap 1B. Oh, there's a cell, that's cell 2. So it automatically does it. And you simply pull the trigger to start the measurement. And it will test batteries up to 15 volts DC. When you're done, you close the test. You can view the data as text on the screen or graphically to easily see anything that may be out. And you can transfer the data to PowerDB as well. And the unit has a built-in spectrum analyzer, so you can see where the majority of your frequency or noise is. And like in this case, I see it's at 100 hertz. This is a 50 hertz system they're on, 50 hertz charger. And I'm seeing it double. That's about what I would expect. If I see it sitting at 50 hertz, I know there's a problem at the charger. The charger has an open diode in it or an open rectifier. So that will show me that problem right off. And I have found that quite often at times where on problem strings. Now, PowerDB. PowerDB is a software that allows you to transfer the data and create custom reports. You can input your logo. You can choose what charts you wish to view. It will also automatically calculate the baseline for your string the first time you do that test. So you don't have to worry about that. It will throw out any outliers and calculate the baseline, which will be used for all additional tests. Or if you already have a baseline, you can enter that as well and use that one. In addition, you can select the cell chemistry and it will automatically fill in the limits for you so that you don't have to wonder, well, how much my deviation from string average do I have to worry about? These get automatically populated so that you can just see the charts and easily see what's good, what's a warning, and what is an alarm. And really quick, let's go over maintenance schedules because we're over budget here on time. Is VLA, okay? This right here, I'm showing minimum and recommended here. And the minimum is really based on NERC requirements, which is the North American Electric Reliability Council, where the recommended is really based on IEEE standards. If you'll notice, most of the tests are pretty much the same. However, what you're seeing is a difference in how often they're done. So really what you want to do is determine how critical the string is, what sort of budget you have for maintenance, and pick a maintenance routine that's between the minimum and recommended, somewhere to fit your needs. For VRLA, you notice it's the same thing. However, you do have some different tests, and you do have different periods of time that you're doing the testing. Also, NiCad batteries are in here, and now NiCad batteries do always require a discharge test because of their profile, but the impedance test also can be done to look at your float voltages, your strap resistances, and it will find batteries that have gone bad. What basically is with the NiCad battery, because of the alkaline electrolyte, when it dies at the end of life, it goes very high impedance. So you'll see that immediately. However, if you get a good impedance reading, it doesn't necessarily mean the battery is good. So that's why you always want to do a discharge test every 6 years to be on the safe side. And with that, this is the contact information, and we're ready for questions.
Yeah, excellent. Thanks a lot, Andy. So we've officially concluded the presentation portion of our second segment. We'll take a few minutes to answer as many questions as we can. We are a little bit over budget on time, but we're going to try and knock out a few of them before we sign off. For those of you that are leaving, when you close the webinar window, a brief survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future seminars. On that survey, there's a field where you can also request a demo or a quote of any Megger products. A copy of the presentations, along with a link to the video recording of this webinar, will be emailed to everyone in about 2 business days, along with a certificate of attendance. So let's jump into a few questions real quick. Our first one I'm going to send over to Volney. Volney, why does the water in a battery evaporate? Could that be the charger?
Okay, so definitely that's an effect of the operation of the battery. While the battery is being charged, these will generate temperature increase, and as the temperature increases, of course, that will generate evaporation of the water in the battery. So this is normal during the kind of a recharge process. And if the float settings are not correct, the battery will be kind of permanently overcharging, and that will accelerate the gassing process, the evaporation process. So on VLA batteries, vented batteries, it's probably not a problem. You go and replenish, although it's not the preferred thing. If you have to replenish water very frequently in a battery, it means that you might be overcharging. And with VRLA batteries, the valve regulated lead acid batteries, you don't have the option to replenish the water, although the water might be still be gassing. So the idea is that the VRLA batteries will recombine these gases and they will become part of the electrolyte again. But if they exceed the pressure release limit, then that water that is being evaporated, there's no way to replenish it, and that's when you get into those dry out process or dry out condition that Andy explained before. So as I mentioned in my previous presentation, operation of the battery affects the life, and this is one of those settings that you want to always be checking, and that's why during maintenance activities you want to measure that and verify that you have the proper settings, so you don't end up drying the cells or have to replenish water that often.
All right, thanks, Volney. Sanket, the next question is going to be to you. Why do we use the term impedance in a DC system? Would it simply be resistance instead?
So when we refer to a battery as a DC system, what we are saying is that the battery supplies DC current when it's put into operation. So when it's connected to a load, the load would be getting a DC current. That's what it means when we call it a DC system. But that doesn't necessarily mean that the battery is just a resistance. When we talk about testing on batteries, we are talking about injecting a current or drawing a current, as is the case with measuring the internal resistance of the battery. But when we talk about impedance testing, what we are saying is that we are injecting an AC current through the battery, and we are measuring the impedance of the battery because we are injecting an AC current. Now, the impedance, as Andy mentioned earlier, is because of it having a capacitive element to it. So that's the difference between that. When we refer to it as a DC system, we're talking about the operation, the way the battery operates. But when we talk about testing on the batteries, impedance testing specifically, we are injecting an AC current through it.
All right, thanks. Our next question is going to be over to Daniel. Daniel, can you equalize VLRA batteries?
Okay, yes, that's a short answer, right? There is yes with an asterisk. As you know, with this type of batteries, VLRA, you cannot replenish the electrolyte. You don't actually have the possibility of checking even that the level of electrolyte. So the general recommendation is that you make sure you check with the specific manufacturer of the battery if you have this type of RLA batteries. The reason is, again, because you cannot check or replenish the electrolyte, you run or have the possibility of drying out the electrolyte. So again, when a manufacturer does, let's say, approves the equalization of that particular model of battery, they typically would recommend less often, or again, some models, some manufacturers will say in the manual that this equalization is not recommended for that model. So in summary, just make sure you check the maintenance manual for the battery in question.
All right, thanks, Daniel. Andy, then your next question is, I've heard that lithium-ion batteries tend to overheat and are prone to explosions. Are there new technologies regarding safety to incorporate more safe measures in lithium-ion battery technology so it can be used in more station service and UPS telecom applications?
Okay, well, when we're talking about lithium-ion batteries, there's many, many different types. Now, a lot of press has been given to this every time one blows. Now, like when we look at commercial pieces of equipment like a phone, they have a gel type battery that's in them. And when they overheat, they get hot enough, they can reach an ignition point, and they're going to swell up under pressure and ignite. They have to get hot enough to do this. Now, when we talk about batteries we're going to be using in UPS or telecom applications or things of that nature, we're really not going to be using those type of batteries. We're going to be using prismatic batteries, which have the cells in them. And those will have BMSs in them. And those BMSs are supposed to monitor and maintain the charge and discharge rates and temperatures so they don't overheat. Now, with that said, can they overheat? Yes, there's no absolute. They can, however, the BMS is a good protection for it, and different chemistries will have higher ignition points to them. Okay, and so as long as the BMS is operating and you're using, if you're concerned about safety, make sure you get a chemistry that has a higher temperature ignition point, because it'll be much less likely to go into that catastrophic failure mode. Now, also with that said, keep in mind, this is a new and evolving technology. All right, so there is no real set maintenance on this. So if you do go with this, you want to carefully think it out and determine what type of maintenance you really want to do on this, okay, to monitor it, because you will have SEI buildup, and if that's not uniform, you can get dendrite formations on them. So just food for thought on that.
All right, thanks, Andy. Volney, our next question is to you. Does battery ground have impact on battery life?
Like many answers on batteries related to batteries, the question is it depends. So what a ground fault will cause is like a permanent circulation of current to ground, and if the fault is in the DC system outside the battery circuit, the string, then that current may be supplied by the charger, so the battery won't see an effect on that, or won't be affected by that. If the fault is anywhere in the battery string, let's say that there's a leakage of acid, and that is creating a circuit to ground, or for any reason somewhere in the middle of the string there's a ground fault, then the current will be circulating from the battery. And in that case, if the battery is providing current, although it's minimal, that has to be supplied by the charger, so the battery will be kind of on a permanent charge instead of a floating condition. And well, remember, these are station batteries, are stationary batteries, are batteries that are there to be on a float condition and operate occasionally. So a permanent flow of current may end up affecting the life of the battery. So it's very important to fix any ground fault that you have in the system, to avoid them, and especially if they are in the battery. Now, if you get to that point that the ground fault is in the battery, there might be bigger problems than the ground fault, probably.
All right, thanks, Volney. St. Kit, the next question is for you. How do we properly do a float current test?
So as I mentioned earlier, float current is a small amount of DC current which flows through the battery when it's in float condition. So if you have a way of measuring the DC current, typically the charger itself shows you the float current on its display, or if you have a DC clamp on, which you can use to measure a current in milliamps, that can be used. As far as our equipment goes, the byte 3 can be used to measure the float current on the system, but again, the magnitude whether an instrument will measure or not will depend on the magnitude of the float current. If the float current magnitude is insignificant, then it won't be picked up by some instruments. So it comes down to the level of the float current that exists and the instrument that you're using.
Thanks a lot, Sanket. Andy, our next question is for you. Is the impedance test appropriate for NiCad battery strings?
Well, NiCad batteries, they have an alkaline electrolyte which gives them a different discharge profile than lead acid. When you discharge a lead acid battery, the voltage slowly drops over time and the impedance slowly goes up. So you can get a very good profile throughout the entire discharge. However, in a NiCad battery, as it discharges, the voltage stays rock solid till the very end, then it drops off and the impedance shoots up. So basically, it's not the only test you want to do. So if you're doing an impedance test on a NiCad battery that's at end of life and its impedance is shot up, yes, it's going to show you have a bad battery. However, if you get a good measurement on a NiCad, low impedance reading, it doesn't mean that battery is good. Okay, it could be close to end of life and you don't know it. So that when we're maintaining NiCad batteries, there's a lot of things we want to do. We want to look at voltage. We want to look at their the strap resistance. We want also the discharge test. However, the products like the Byte 2, the Byte 3, when you use these, when you use like a Byte 2 with a NiCad battery, you go through the string, you're going to get everything in one pass. So you'll get the straps, the resistance, and if you see high impedance values, that's a sign that the battery has a problem. But if they're good, it doesn't mean they're, if the impedance is low, it doesn't mean they're good. You still want to do a discharge on them.
All right, Andy, thanks a lot. Daniel, next question's for you. What about the frequency of visual inspection? Is it important when we record the cell voltage each week?
Sure thing. And in terms of the frequency, as I mean, to paraphrase Bolney, it depends, right? It depends on the type of battery question and also what body you are adhering to in terms of the standards, right? In our realm of applications, stationary batteries and the substation, we have the IEEE, the NEDA, and even the NERC documentation. So rather than just telling you, a frequency for a couple of different batteries, I would refer you to, we have a very good document in the Megger website comparing not only recommendations in terms of visual inspection, but for any test related to batteries. Again, comparing the recommendations from NEDA, IEEE, and NERC. That document will have two separate tables, one for BLA and BRLA, and a second table for NiCad batteries.
All right. Sanket, our next question's for you. When testing NiCad battery straps, do we need to take the battery out of the string?
So Andy kind of went over this while talking about impedance testing on NiCads. It depends on the way on the equipment actually that you're using to run the test. If you use the Byte 2, for example, it injects current through the whole string. So when you're taking measurements, if you have stainless steel hardware on which your probes are placed, since there is no current flowing through the hardware, you can still end up measuring impedance on the NiCads and strap resistance as well without any issues. But if you are using an instrument in which you have to inject the current through the stainless steel hardware, then that makes it difficult for you to get the actual strap resistance or the actual impedance of the NiCad, because the resistance of the hardware itself is pretty high as compared to those elements. So it comes down to the technique, the method that you're using. Ideally, the best way to do it would be to use an instrument which injects the current through the whole string and then measure the voltage drops across different points to get the strap resistances and the impedances.
All right, thank you. Andy, Can the PowerDB software be used with a byte 2P? My byte 2P is about 17 years old.
Yeah, the PowerDB is designed to work with the byte 2P. Now, one thing to be careful of, if it's 17 years old, now keep in mind, the byte 2P consists of a transmitter and receiver. So you want to make sure that it really comes down to the receiver that's going to be communicating with the PowerDB. So you want to make sure that is a byte 2P receiver and not an M byte receiver. If it is, then you may have some issues communicating. But other than that, if it's a byte 2P receiver, it should communicate with it. You may need to get a firmware upgrade depending on how low the firmware is.
All right, thanks, Andy. So while I have you, the next question is also for you. Oh, sorry, Sanket, I had lost my spot. Sanket, your question is, I missed what creates the ripple current and why is it occurring? Could you go into that a little more?
Okay, so the ripple current is the AC component which can be seen on the battery string, and that occurs that can exist because of the condition of the charger. So the charger is what keeps the battery charged by applying a DC voltage. But if there is problems with the rectifier circuit on the charger, then a certain amount of ripple can come through, and that ripple current magnitude, if it's significant enough, uh, a limit to consider would be 5 to 7% of the capacity of the battery. So for example, if you have a 100 amp hour battery, if the ripple current on the battery string is more than 5 amps, then that's considered a significant value. And what it can do is it can lead to deterioration of the battery, because it's kind of it kind of leads to discharging of the battery over each cycle, because since we have an AC component now in the system, as the AC wave changes, as it goes to positive peaks and negative peaks on each half cycle, that is leading to discharging of the battery on every half cycle. So it can lead to deterioration of the battery. So you need to pay attention to the amount of ripple current that's present on the string. And the difference between float current and ripple current is AC and float current is DC.
All right, thanks, Sanket. Andy, the new station battery systems I'm seeing installed have more and more insulation around the posts and straps. What do Megger offer to enable measurements to be taken with the new setups?
Okay, we are seeing some battery manufacturers that are doing this for basically for safety concerns. They want to have it where you basically you'll see caps on it may only have a small access port in them. And we actually offer adapters that will go through those access ports, so you can take those measurements. Now, however, one thing to keep in mind is that if you are using these batteries in substations where NERC rules apply, you must be able to get to the post based on your NERC requirements. So if these type of setups don't allow you to get to the post, you cannot use these batteries in substations where NERC applies, and that will be any substation that connects, that has a protection equipment that connects to the bulk system.
All right, thanks a lot, Andy. I'm also going to throw the last question over to you. What is the recommended charging current during initial charging of a battery?
That's really that's right up there with the most common answer, depends. So really, when you're getting into that, you really want to contact a battery manufacturer and make sure that you're following their recommendations to do this. That's really the best method to use. It's just follow the battery manufacturer's recommendations.
I can add to that. Typical values which are seen for vented lead acid is 7% of capacity. NiCad is 20%. Sealed lead acid is 10%. But as Andy said, it's best to contact the manufacturer. But these are the typical values that are seen for different battery types.
All right, thanks, guys. I really appreciate it. I appreciate our presenters and our panelists and our attendees for joining us today. We have drastically gone over time, but I appreciate everyone sticking with us. If we didn't get your questions today, we will be following offline. We will follow up with you offline in the next couple of weeks. But thank you all again for attending. Please remember to answer the survey. That survey will also include a field for you to request a quote or a demo of any Megger product if you're interested. I look forward to seeing everyone on part 2 tomorrow at the same time, 1 p.m. Central Daylight Time. If you have any questions, please feel free to reach out to our email at usasales@megger.com. And I will see everyone tomorrow, and have a great rest of your day, everyone.
Thank you.